We're going to discuss how the properties of an exact differential are used to derive Maxwell relations that are important in thermodynamics. So let's first look at just a generic exact differential. Differential of C in terms of two other variables, A and B. And we're saying this is exact, which means that this term R is the partial of C respect to A at constant B, and it means this is the partial of C with respect to B holding A constant. And so these partials mean if we were to make a small change in A while keeping B constant, this would tell us how C would change. So if we use a specific example, if C is 2A squared times B plus B, then the partial of C with respect to A at constant B would be 4AB plus 0 because B is constant. And the partial of C with respect to B holding A constant would be 2A squared plus 1. Now suppose we wanted to differentiate again. So what I'm going to do now is differentiate respect to B, this term, derivative of C with respect to A at constant B. Now I'm going to differentiate respect to B and keep A constant. So that's the derivative with respect to B of 4AB, keeping A constant, and this is going to be 4A. Likewise, can differentiate respect to A of the derivative of C with respect to B at constant A. And now when I do this differentiation respect to A, I'm going to hold B constant. So this derivative with respect to A, and up here we see that this derivative 2A squared plus 1, we're holding B constant. This is 4A. So notice we get the same answer. And this is because this second derivative, it's derivative with respect to B, derivative with respect to A, and this one here is second derivative of C, respect to A, and respect to B. So changing the order of differentiation shouldn't matter, and it doesn't. For an exact differential, we get the same answer. And we're going to use that in terms of deriving Maxwell relations. Now if we go back and look at our equation, what this says in our original equation is derivative R respect to B, constant A, is the same as the derivative Q respect to A at constant B, because this is what we just did the calculation for. Remember, this is R and this here is Q, and we showed those were equal. And so this gives us a Maxwell relation. So now let's apply this idea to a thermodynamic equation. Let's use differential internal energy, T ds minus P dV. That's where we're going to start with. From what we've just said, if this is an exact differential, then T is the partial of U respect to S at constant V, and minus P is the partial of U respect to volume at constant entropy. So what we're going to do is take the second derivatives like we just did. So the derivative of T respect to volume, keeping entropy constant, should be the derivative of minus P respect to entropy, keeping volume constant. So then we say partial of T respect to V at constant entropy is minus the partial of pressure with respect to entropy at constant volume. So this is a Maxwell relation that results from this property of exact differential.